Okay, we will now do problem 23 of section 3.4. So, this is again a problem on indexed families of sets. So we have I, a non-empty set of indices, and two index families, A sub I and B sub I. So there are two parts. The first part is to prove an inclusion. So it's to prove that the union for little I and capital I of A sub I minus B sub I is contained in the difference between the union of the AIs and intersection of the BIs. Okay? So, again, let me start this proof without even thinking much about it, because there are lots of things that we can already do. There's just standard, okay? So you don't have to think much about it. I want to show a containment. To show a containment, we take an arbitrary element of the first set and prove that it is in the second. Okay? So I can start with let little x be an element of the union of the differences. Now, your goal then is clear. And again, if you want to, you can put a parenthesis here. Need to show that this same x is on the other set. But this, would be for emphasis, is not necessary. But also, something that I know that I have already to do is to interpret what this means. What does it mean to be in this union here? So we can say, hence, it means that there is some index, and I can call it I sub 0, for instance, such that x is in that particular indexed difference, right? So I have, hence, there is I sub 0 in I, such that x belongs to A sub I0 minus B sub I0. In other words, x belongs to A sub I0 and x does not belong to B sub I0 by definition of differences. Okay? So far, haven't really thought about the problem, just follow the usual steps. Now it's time for you to look at where you want to get. So you want to get that x belongs to the difference between the union of the A's and the intersection of the B's. So, you also have to understand what it means to be in there. So you write it explicitly. So I have to have that x is in the union of the AIs, and x is not in the intersection of the BIs. Okay? So you have two things to prove. Now, what does it mean to be in these? So that means that there exists some I. So, and I should be careful because I don't know if it's I0 or not. So maybe I should call it something different. So there exists some I sub 1 such that x belongs to A sub I sub 1. That is the first statement. And here I have a negation. To be in an intersection, so this, let me write in two steps. You don't have to, if you're already familiar, if you're comfortable with these sort of things, you don't have to write in two steps. But it's saying that it's a negation of x being an intersection. And what it means to be in an intersection means that it is in everything, every single one of the B sub i's. Right? So these would be for all little I in I, x belongs to B sub I. But the negation of these, of course, is going to be there exists. So there exists And here, let me not call it I0, let me not call it I1, so let me call it I2. Here I should probably bound this quantifier, so it's, although that's clear that that's the universe for that variable, but we should perhaps be careful. So I'm saying that there exists an I2, an index, such that X is not in BI2. So you see, whenever you go to there exists, I usually don't use the general variable for the index because it's a particular one. When you say there exists something, it's a particular one. So you don't want to call the variable that you're calling everything, perhaps. All right. So here is what we have. Have there for some index I0, X is in I0 and X is not in BI0. Here's what we want to show. There exists some index I1 such that X is in AI1, and there exists some index I2 such that X is not in BI2. Okay? Notice that if you're a bit careless in here, if you had called this I1, then you'd be under the wrong impression that it was necessary for these two indices to be the same, which is not necessarily the case. Okay, so if you had again, is that the problem of repeating letters. But all right, so if you look in what we have, so we have that X is in some A sub I0 and it is not in some B sub I0. And want to show that X is in some A sub I something and it is not in some B I something. Well, but we have it. And again, if you think about it, what indices do I have to use? So there exists, you sort of have to, not always, but lots of times you have to come up. Take this index in here. There exists an index, here it is. You show it, I mean you come up with it. What indices do we have in here to use at all? It's a completely abstract set. Like I said before, you cannot say take I equals to 0. You don't know even if 0 is in the index set. We don't know what the index set is and is abstract. There's only one index that you know even exists. Maybe there's only one index, this I sub 0 in here. That's the only one you even know exists. So if you want to come up with indices in here, your hands are tied. But that helps you because now you know what they should be. And indeed, of course, I0 works for both. Okay? In any event, another way to even see that is the following. So you see the fact that X belongs to AI0 implies that X belongs to this union in here. Okay? Which is related to these, right? It's exactly this interpretation in here. So let's say like this. So since X belongs to AI sub 0, we have that X belongs to the union little I in I of the A sub i's. This is by definition of the union, right? It's exactly the definition, as you can see, that we interpreted here. Okay? Also, since X is not in B sub I0, we have that X is not in the intersection of the BI's. Because again, to be in the intersection, you'd have to be in every single one of them, but it is not in at least one of them, so it is not in the intersection. So hence, X belongs to the first, does not belong to the second, it belongs to the difference. So it belongs to, union of the AI's and is not in the intersection of the BI's. And I'm done, right? I took an arbitrary element of the first set and showed that it is in the second set. So I proved the containment of the first in the second. Okay? Now, part B is one of those. it's hard to see if it is easier or harder than part A. It depends on how creative, how much you can visualize, how much you can see what's going on, how much intuition you have in this problem. If you have some intuition, this is fairly easy. You don't have to come up with a proof. You have to come up with an example. On the other hand, this can be hard because it really depends on you having some sort of idea where to go with these, what you should be doing to come up with the example. And unfortunately, it's one of those things I cannot give you much advice on how to come up with these examples or counter examples. I mean, something where something fails. So here, this problem is to find concrete examples where you don't have equality. So this is saying basically that you don't always have the other containment. The first is containing the second, but it's not necessarily true that the second is containing the first. Okay? So you have to stare at these expressions and try to see, get some intuition on what's going on. Again, there's no clear path on how to do that, but what sort of made me think of my example is the following. So if you in here you see you're taking things from every single A, but in here you first put every single thing that is in the A's together, and then you just take the intersection. But this intersection here can be small, could be conceivably even empty. So maybe you're not taking anything of the A's if this would be an empty intersection. So you have all the A's. Where in here, you might be actually taking things out, right? Because you're taking things out from each single individual set. Now, I don't know if this helps you at all. It's a vague reasoning, but that's what came to my mind to come up with my counterexample, which it took me it was not immediate. It took me a couple of minutes to actually get a working example that is very simple, but here it is. So one example. There are many examples that work. So here, my example was by the way, so these might seem even more complicated because of these being families of index families. Usually what you should try to do is make a very small index family. For me, there are only two indices, 1 and 2, so only two sets in each family. So, and you should try, if you're coming up with counterexamples, try to use simple families, of course. So okay, so I have only two A's and two B's. So what are my A's? I have A1 is 1, 2, and B1 is only 1. And I have A2 is 2, 3, and B2 is only 3. So now the claim is that these sets are different for those families. For those two families, the A's and the B's, and you just compute it. So here, what is this union of the differences? So here the difference, A1 minus B1 is just 2. What is the difference in here? Well, chance that you're just going to stumble by trying things on something for which you don't have the equalities, since you know that they're not supposed to be equal. Okay? So this is problem 23 from 3.4.